Thank you for having me as well. I appreciate the opportunity to be here and talk to you guys, like Sultan said, about some of the big advancements we've made so far in our field. And specifically, as was mentioned, I study galaxies in the early universe. And so my flavor of astronomy is really exploding right now. JWST is kind of the telescope we needed. So what I want to talk about today is in my specific field of astronomy, where do we come from and what have we gained and where maybe are we going with the data that's coming in from this telescope and the discoveries that are being made. And so that's in exploring the early universe. So galaxies very, very long ago, over 13 billion years ago, and understanding them in context and in details that we previously were unable to do. So when I say the early universe, what does that mean? Here is a really great kind of illustration, so to speak, of cosmic history. So on the left, you have present day, and on the right, you have the Big Bang. And here we see at the bottom, redshift and time since the Big Bang. So redshift is a way we measure time that has passed and how far away something is or how long ago the light left it. And so as redshift increases, time is going back towards the Big Bang. And so we're looking at more distant objects, meaning things that light left billions of years ago and traveled to us throughout that amount of time. And the early universe is in this case, we're talking about the first billion years, so to speak. So before, with ground-based telescopes, we were able to see back maybe to redshift 1, or roughly half the age of the universe, 6 billion years ago, as you can see. And Hubble was a beautiful telescope that really unlocked a lot of our understanding of the universe around us and information about galaxies outside of our own. And so with Hubble, we were able to see quite far back, especially when it got upgraded to infrared cameras. And we're able to see further and further back. And I put a nice big current over JWST as that's pushing the boundary of our ability to study the early universe, largely due to the wavelength coverage that it gives us. And so how do we use these telescopes to find early galaxies? This is a great video as well. It illustrates at the top here, these are filters for Hubble. So these would be the actual images that we would have gotten with the Hubble Space Telescope of a galaxy. And what we're taking is just a simulated galaxy and we're pushing it further and further away from us or earlier on in the universe. And so this gray shaded region across the top is actually the light emitted by this galaxy. And as you look at galaxies further and further away, of course, it gets fainter as more distant objects are fainter. But what we also see is that there is a break in the emission from a galaxy. And where this break happens tells us a lot of information about the distance of the galaxy, but also some physical properties of the galaxy and the universe. But how we find distant galaxies is we look for this break. So as you see, we push it further and further back. Each one of these images, the galaxy actually drops out. We call it a dropout band, where we no longer see the galaxy in that filter. And so whichever the specific filter the galaxy drops out of gives you an estimate of how far away that source is. And so we were only able to study these distant galaxies with one image prior to JWST if we were looking for some of the really early galaxies. And with one image, you have to be very sure that what you're looking at is an actual galaxy and not something else, or some nearby galaxy that looks similar to a distant galaxy. And so what we did prior to JWST is we used the Hubble Space Telescope in tandem with the Spitzer Space Telescope, which I'm showing here on the right-hand side, which is a pretty low resolution comparatively, but it works at longer wavelengths. And so if pushing this galaxy further and further away from you, or you're looking further and further away, these galaxies drop out of the filters. This is because that light is shifting as it's traveling to us. So even this ultraviolet light from galaxies is being shifted, this break is being shifted into longer wavelengths as that light stretches over time on its journey to our telescope. And we need an infrared telescope to see the UV light from galaxies that are in the early universe. And so Hubble had a little bit of infrared capabilities. Spitzer was an infrared telescope. And so here I'm showing a few galaxies that we selected from a lot of data using Hubble, where as you can see, they do not show up in the shorter wavelength filters, but you do start to see them in the longer wavelength filters. And then again, we see them in Spitzer, except for it's very difficult to kind of disentangle some of the light from the Spitzer telescope at this low resolution. And so this is how we selected galaxies, and we looked for distant sources in the universe by looking for this dropout feature that we see in our images. But in order to accurately measure the distance to a galaxy, you really need a spectrum, because while this break is at a specific wavelength, the filter in the imaging is quite wide. And so there is a range of redshifts in which that particular filter would be a dropout. And so you need an actual very specific measurement. And with spectra, this is an example of a simulated spectrum of an early galaxy. In this case, this is at redshift 7.5, where you see a lot of emission line features. This is coming from the star formation in the galaxy. And if you can measure a specific emission line from a source here, then you can actually measure a very specific distance, where you have an estimate of the distance based on the width of the filter here shown below. You get a very specific measurement of the distance. And this is what we call a spectroscopic redshift, by using the spectrum of a galaxy, instead of a photometric redshift by using the photometry or the photos or images of a galaxy like I showed earlier. And so unfortunately, in the early universe, there was not necessarily the technological capability to study these galaxies with spectroscopy easily. And as I'm showing here at the top, about here, this is the last filter, the last wavelength coverage that we have in ground-based spectroscopy in the infrared. And this is with the Keck Observatory on Mauna Kea in Hawaii. The rest of this portion of the galaxy spectrum, the rest of the light these galaxies emit and all of the information contained within, is completely invisible to us. These filters I'm showing here in the yellow and orange are actually the Spitzer imaging filters. We just had no spectroscopy that we could do or see any of these details from these early galaxies. This is all we could see. And unfortunately, while this emission line is incredibly bright in a lot of star-forming galaxies, it would be the easiest one for us to detect in these sources, because of reionization, which is a process during which all of the material in between galaxies in the universe went from being neutral hydrogen, which is here shown in the white, to ionized hydrogen, which is shown in the black. This is called reionization. It's ionizing the hydrogen molecules, and the light is actually blocked by neutral hydrogen. As you can kind of see in this illustration, this is a good figure made by Inte Jung in his paper in 2022, where if this ultraviolet light, or say, for example, that Lyman alpha emission, that wavelength of light emits from a galaxy, the neutral intergalactic medium, or IGM here, is eating up all of that light. And so even if the galaxy is emitting it, we cannot see it. It does not make it to our telescopes. Perhaps if you have a galaxy large enough, surrounded by a lot of other galaxies large enough that they've made an ionized bubble around them, the light will be able to get through because it will shift in wavelength to a longer wavelength in this travel time distance. We see Lyman alpha very, very common and very bright from most galaxies in the universe that are forming stars, but except for this neutral hydrogen during this period of reionization is actually blocking a lot of that particular light. So while we are able to see the galaxies in images, getting spectra of these sources when the wavelengths that we can only see include Lyman alpha, which is actually blocked by the universe that these galaxies live in, made this process incredibly difficult. So like I mentioned, the Keck Observatory is one of the largest telescopes on Earth. It's a set of twin telescopes here. And this is an example of one of the galaxies that was actually found to be record-breaking in 2013 by my PhD advisor. And that's this one right here. And so while this line is incredibly bright in star-forming galaxies, if it can't quite get through all of that neutral hydrogen in the universe that the galaxies themselves live in, it gets kind of attenuated, or it's fainter than it should have been, given how much was emitted by the galaxy. But we were able to do this. And so here I'm showing several examples of actual data detections of this Lyman alpha feature, even into the heart of reionization. So these are redshift 7.5, which is the one I showed you just a second ago, and 7.6. So we're pushing further back into this period of time where there's probably more neutral hydrogen. In fact, the record-breaking spectroscopic redshift from the ground was this redshift 8.68 galaxy by Adi-Zitrin in 2015, also using the Keck Observatory. So part of my PhD was in an effort to maybe see if we can push further. If we can see 7.5, maybe we can see redshift 9, or even more of these sources. And so this is an image from Hubble here in the background, and I'm pointing where the sources are that we were looking for with the Keck Observatory. And so this is that source that Adi-Zitrin in 2015 found, and it was at this redshift 8.6. And if we could mute, please, that would be great. So if I targeted a lot of sources in the field called EGS. This is this field here in the background that we studied with Hubble, and I was also able to detect another emission line, another Lyman alpha emission line from a source at redshift 8.6. And so what's not only interesting is that we are able to do this from the ground with a lot of time and many years of effort, but these two galaxies are actually physically quite close to each other, which means that there's more galaxies at that particular redshift than we would have expected theoretically, and it's an overly dense region of the universe, which we would call an overdensity, which could also, as in that figure before, be why we see Lyman alphas. If there's a bright galaxy with a lot of other ones, they've made an ionized bubble large enough to see them. So this is kind of the extent of what we could do prior to JWST. This was the best that we were really able to do, but with imaging, we were able to do a lot of really great science. And so the Hubble Ultra Deep Field is a very small spot in the sky that we pointed the telescope at for many, many thousands of hours. And we actually found 10,000 galaxies in this image. And so everything in this image you're seeing that doesn't have these little spikes is a galaxy. These ones with the spikes are actually stars in our own Milky Way that are just photobombing, are in the way of our images here. And so this is just for scale, the size of the Hubble Ultra Deep Field compared to the moon, if you were to look up on the sky, and there are 10,000 galaxies here in this particular spot. And so we're finding a lot of galaxies with Hubble, but a lot of them are quite faint and far away, and we wanted to be able to really confirm them. And so how far did we actually get? Here is that redshift 8.68 source. So here in this heart of reionization right here, going back again to the Big Bang on the right and the present day on the left, this was that source that was found at the Keck Observatory, but Hubble actually has a spectrograph on it that was able to detect this break in the continuum in a galaxy at redshift 11. So this is GNZ11, and at the time was the record-holding galaxy as far as how far back we were able to detect and spectroscopically confirm this source. And so we have a handful of galaxies. I showed you a majority of the ones we knew about in the early universe, including 2 right here, and then several more at this range, and pretty much only 1 that we'd confirmed here, with a lot of other imaging candidates here that we were unable to get spectroscopic redshifts for. So now we have JWST, and here what I like to show is actually a calibration image. And so when they first launched the telescope, it had to unfold in space, and it's a beautiful giant space transformer of a machine. And when they wanted to make sure that all of these individual mirror segments were lined up and focused such that a star or a single point of light would look like a single point of light, plus all of the diffraction spikes here, this was just a test image they took for a couple seconds to make sure that everything was focused down to the star being a single point instead of seeing multiple images of it. The mirrors were all aligned. And I really like showing this image because everything in the background is actually galaxies. This telescope is incredibly sensitive, such that even when we're trying to just do things to calibrate the telescope, we are still getting data of galaxies that are outside of our own and far away enough that we just didn't necessarily know about before, but also are getting, kind of bonus data in the background of all of these detections. And so one of the first things that we pointed JWST at was this EGS field, the field I showed before that had these distant galaxies in it. And the CEERS collaboration was the one who had the data over this particular spot of the sky, and it's a collaboration that I am part of. And so just to kind of illustrate, what did we gain as far as the images that we get from JWST from what we had with Hubble and Spitzer? So again, this is one of those galaxies that we had identified where we did not see it in the shorter wavelengths, and we start to see it in the longer wavelengths of Hubble, and that we also kind of had really, really low resolution images from Spitzer of this source. And now as we go from left to right, we're going from shorter to longer wavelengths. And we try to put the JWST images kind of in the correct place as far as wavelength coverage goes. And so we have really good resolution as well at these wavelengths here. And we have a bunch more that we did not cover before. And then we also have really good resolution at these wavelengths that Spitzer covered as well. And so this is this same source, but also including all of the JWST images. So in cases where we only had 1 or 2 images to go off of, now we have a whole lot more that we were able to use. And this is a much better way for us to identify these distant galaxies. And we have a lot more resolution and wavelength coverage than we had before. And this is another example just to kind of show you the improvements that we've made technologically with JWST. And so here on the left is a combined color image of Spitzer. So those 2 filters that I showed you before, plus the other 2 that the telescope had. As you can see, we do have some information, and this was phenomenal when this is all that we had at these wavelengths to study these galaxies. But it is quite low resolution, and it's not very sensitive. It also had quite long resolution, quite long wavelength images as well for a short period of time. And again, these are quite low resolution. Each one of these squares is a single pixel. And so here we've made a combined color image with the JWST MIRI instrument, which is a camera on the telescope that has longer wavelength than NIRCam, which is what I showed you previously. And it has all of these wavelengths as well. So kind of in between the 2, slightly overlapping. But this is the increase in resolution and sensitivity. There are faint things in the background here that please turn your screen brightness up at any point, because these are quite dark images. So hopefully they can come through. But these faint sources here in the background, and you're also being able to resolve a lot of the individual sources that were quite blurred together before. And so we have increased resolution, higher sensitivity at all wavelengths that JWST can observe at. And this has been incredible to just see, but it was also scientifically quite interesting. So for example, these galaxies I showed you before were just a tiny, tiny dot in the Hubble images. And I'm just showing you a very busy plot to overlay. Again, this is the EGS field I showed before, and those 2 sources. Just for example, this is all of the data we got from JWST from the CEERS collaboration. But for example, those little tiny dots that we saw in Hubble, with JWST, the increased resolution actually shows us that there are multiple parts to these sources. It's not just one tiny galaxy. There's actual shape, structure. There's morphology is what we would call the actual shape and structure of a source. And there's also differences between different parts of these galaxies. And here we've made a color image with it. So our increased resolution is doing a lot of things. And here's another great example of that. In 2012, Dan Koh also found a galaxy that we selected photometrically to be at redshift 10.7. And here again is this source. It's assisted by gravitational lensing. And so this is a cluster of galaxies whose gravity is so strong, it's warping the light from sources behind it. And it actually imaged this source 3 different times. And so this is the same galaxy. We just see 3 different copies of the image. And as you can see, this is just a tiny little red blob. And with all of our modeling, we predicted that it would be at a redshift of 10.7. We also got data for the same cluster with JWST, and I highly encourage you, if you have time, there's a press release about this, and you can kind of click back and forth between the 2, and you'll see there's a lot of things that just pop out in the JWST images we never saw before. All of these sources are incredibly detailed, and also were invisible to us with Hubble for a variety of reasons. But in this particular case, this same galaxy was, lensed as well, still in the same way. And we find that that it's actually two galaxies and not just one. So this increased resolution shows us a lot of detail. There's two galaxies, or maybe one with two components that are interacting. And so this could be why this is so bright, is in fact it's two instead of one sources. And so we actually still continue to get a redshift for this at 10.6 with the new JWST images. And if you're interested, we do have for the CEERS program specifically, we've released a big press release with NASA, the color images of our NIRCam field. And so you can download these. I highly recommend you do this with a computer and not on your phone. They are quite large. And here we zoomed in a little bit on a couple of them. And this is a website that we wrote up about the first half of our data. This is some of the first images that were released from JWST. This was in July when the data first left the embargo period. We got data that same day. So as you can see, there's some exquisite detail in these galaxies, and you have a lot of information, and it's really fun to just keep zooming in because there's a lot of galaxies in here, but again, very large images. So what did we find? So in the first days of looking at JWST images, and this again is from the CEERS team, which I am a part of, we found this source right here, which we thought was a redshift of 12. We only took 1 hour per filter in this particular survey. And with the Hubble Ultra Deep Field, it is hundreds of hours. And so this is not even a deep exposure or a long exposure for JWST. We thought we'd be very lucky to see something at redshift 10 or 12 in the first few days of our data as we were learning how to process it, and it was brand new to everyone. But we found this source, and all of our modeling and all of our measurements estimated it to be at a redshift of 12. It was quite exciting. In fact, the PI of this program and my PhD advisor, it was his daughter Maisie's birthday when we found this source and decided to write up the paper about it. And so we named it Maisie's Galaxy after her. That same day, some other people were looking at these images as well, and they found a source that they modeled and estimated to be at redshift of 16. We didn't find this because we didn't think that we would see that far away. We stopped at 12 and didn't even think to look for anything past that. And so that was a failure of our imagination. But this is a source that they measured to be at a redshift of 16. And there's a possibility that it could have actually been at a redshift of 5, or a galaxy much closer that mimics the same kind of imaging features as a source at redshift 16, just perhaps it has strong emission line features. And so that's this here at the top. So these dots are the actual imaging measurements that we have for this source. And it could be, like this black spectrum, a distant galaxy where you found this break. It could be a redshift 5 source that has really strong emission line features such that this particular data point is pulled up by it, and this one as well. And so instead of seeing a break, we're actually seeing this slope plus an emission line here. But we don't know if we just have images. And so this could be a source at redshift 5. It could be a source at redshift 16. If it was 16, it would have broken a lot of records. We also had a paper come out of our team where we had this source that could have been redshift 13 or could have been redshift 5 in a very similar way. And the reason that we picked it as redshift 5 instead of redshift 13 was because we had the radio data from previous studies of this field right here that actually helped us determine that it could not have been this really early galaxy at redshift 13. It must have been a redshift 5 source because we see all of this dust. And so we are able to actually see a lot in these images, but we do still need spectroscopy to confirm the distance and kind of disentangle some of this information. What else are we doing in the imaging portion of our studies with JWST? Well, we have the Hubble Ultra Deep Field, and we have pointed the JWST telescope for 24 hours per filter at a spot of the sky, and this is the NGDEEP program. And this is just showing half of our data was taken January of last year, and the other half was taken January of this year, and we are processing it for you to release these images, which will be coming out soon. And so this is the NGDEEP collaboration, to where every single point in the background of this image is a galaxy. every single one of these tiny little points that you can see, please turn your screen brightness up, that you can see is a galaxy. We're able to see so many fainter, further things with this telescope. And again, this is only half of the data, and I'm very excited to very soon release the images of the full data set. Other things that we are working on with JWST is the PEARLS collaboration is working on a time domain deep field. And here are some of the first images from their press release from that. And what time domain means is that in order to get a deep field, in order to see the really faint things and the really far away things, you need to expose for long periods of time. And what you can do is you can do that all at once, like we're doing with NGDeep, or you can do that over time, keep coming back to the same spot and taking more images, and then you keep adding those together. But what that also allows you to do is to see things that might change over time, such as supernovae exploding or objects that are moving around in our own solar system or our own galaxy that we weren't able to detect prior, that have moved since the last time we took these images. And so we're building up a deep field here in the North Ecliptic Pole, which is a spot directly up from where JWST can point that it can see at any time of the year. And so this is another really fun program that's been happening, and data is still being taken for it. And again, some phenomenal images just of nearby sources, because those are the more pretty ones to look at. But this is some of the data that's been taken, and just, you know, the first year of JWST really had a lot of exciting programs to see. One of those was also the Cosmos-Web program. And so while we took a lot of exposures in a very small space to see the faint sources that are really far away with NGDeep, with Cosmos, what we're doing is we're covering a large area of the sky all together in one. And here, this is from the survey paper where we had the first set of data. This is the Cosmos field, which has been studied very well from the ground for decades, and with Hubble as well. This blue shaded region is the entire area that is going to be covered by Cosmos-Web, and this small image I'm showing you is just a very small segment of it. We got the first half of our data last year, and then we got the second half of our data again in January of this year, and so we've been quite busy and in filling out and in showing you the entire area of the sky. This allows us to look for the bright, rare objects where you could see the small, faint things. If you go deeper, if you cover a larger area, you will find the rare objects that are quite bright if you don't have deep images. And so there's a lot of different techniques and strategies in studying the early universe that have been implemented with JWST that we've learned from previous telescopes and surveys of galaxies. And I'm excited to be on almost every single one of these teams and involved in these programs. And so we can find these distant galaxies. We found Maisie's galaxy. We found galaxies that, you know, could have conflicting answers depending on some assumptions, or just the way the actual observations are done, or how the filters line up based on where the emission line features are. So again, I'm going to show you this simulated spectrum of a galaxy to remind you that we want to actually spectroscopically measure the distance to these sources, because that can confirm that they are what we think they are. And then that gives us the go ahead, so to speak, to actually put them in context of other sources that are at that time. If we don't know if a source is a redshift 5 or redshift 13, those are very different times in the universe. And so we can't say something as a whole about galaxies necessarily unless we are able to confirm that they are where we think they are in cosmic history, as well as a lot of other things about them. And so we want to follow these galaxies up and get spectra for them and confirm again the distances. And so while I showed you before, here is about the limit of what we were able to see from the ground, JWST's NIRSpec instrument can cover this entire range of wavelengths at once. And so we are able to see, again, features of these galaxies that we've never seen before, and we get all of this coverage simultaneously from the JWST NIRSpec instrument. And so this is, I'm happy to report, an actual real spectrum of a galaxy. So while this is the simulated one, and here's the Lyman alpha, and we go all the way out to the oxygen 3 over here, this right here is where this particular source stops our observation. So here are those oxygen 3 and hydrogen features, and here is that Lyman alpha emission line. This is a real spectrum from JWST of an early galaxy. And this is that galaxy, again, at redshift 8.68. So this is what we saw with Keck. This is Adi Zitron's discovery of the Lyman alpha line. And this is how sensitive Keck was, and the only part of the spectrum that it could possibly see. And now, not only do we confirm that there is this Lyman alpha detection, but we have a lot of other information about this source. We have measurements of oxygen and hydrogen and neon, and we have carbon and magnesium and all kinds of stuff in the galaxy that can tell us a lot about its physical properties and not just measuring a distance. And so this is really exciting to actually get to see these galaxies in details that I've never seen. I must say I spent my entire PhD looking for this one emission line. And when I downloaded the data for this source, I was like, does someone have a picture of what these lines are? I don't know how to identify which one is which. Can I have a list of what's in galaxies? I only had to know these two. And now there seems to be a lot more lines in my sources. And so it was a great problem to have, but it was incredibly overwhelming, the amount of information that we finally got for these sources. So what about the record-holding galaxy for Hubble, this GNZ11 source? In fact, this spectrum was taken by the JADES collaboration. And when they published this, I cried because this source, this spectrum is beautiful. This is a galaxy at redshift 10.6. This is very far away. This is completely unmanageable from the ground. The Hubble telescope saw this break right here. This little peak, it was only able to see this part. And since we did see a break, we were able to say it was at a high redshift. And in fact, this break is not as sharp as we thought it was. And we thought it was here instead of here. And so that's why we thought it was redshift 11 instead of 10.6. But again, not only are we seeing the break in the spectrum of this galaxy, but we are seeing a lot of really interesting features. And this tells us a lot about the composition of the galaxy, how many stars it makes, what kind of gas and dust is in it, and if there's even other sources of emission than just the star formation in this galaxy. And so we pointed the telescope at a lot of things that we knew about, such as this 8.68 source in the EGS field and GNZ11, these record-holding galaxies from the Hubble time. But what we also were able to do is follow up with the CEERS observations with spectroscopy. In fact, this is Maisie's galaxy. This telescope didn't just find this tiny little dot in our data, but we actually were able to get a spectrum of it. And here again is that break. This is a very faint galaxy. So it's definitely fainter than GNZ11. And we had significantly less time to observe it, but we do see this break. And it turned out the galaxy is at about redshift 12, it's 11.4. And so we aren't just finding these sources, we're actually following them up and confirming them with spectra from the same telescope. And that's quite exciting. And what about the sources that we couldn't tell? What if it's redshift 5 or redshift 6 or 16 or redshift 13 or redshift 5? So we followed up those sources as well with this same program. And we found out that this source that could have been a redshift 16 was in fact a redshift 5 source, or 4.9, that had these really strong emission lines. In fact, these emission lines are stronger than what we expected to see in galaxies at this time in the universe's history. So our models did not include really strong emission lines in our galaxies, which is why we weren't getting the right answers, or we were getting answers that were quite discrepant from each other. In fact, that source that could have been at redshift 5 or 13, and we had thought 5 from our radio data, was also at redshift 4.9. So these two sources, and we found two more, are all really close to each other. They're in the same area of the sky. These two were identified in the CEERS images, and so were these. We didn't know about them before, but there's, again, another overdensity of galaxies. There are more galaxies at specifically redshift 4.9 in this field than we knew about before, and that's quite exciting. And so while we didn't break a record at redshift 16 with this source, we found something very interesting that we didn't know about in the universe, and that we now can incorporate in all of our studies going forward, so that these kinds of confusions are not quite so detrimental to our measurements of galaxies. The JADES collaboration, again, has a lot of time. They are the collaboration that built the NIRCam camera and the NIRSpec instrument. And so they have a lot of time to use both of these instruments. And they did this similar thing where in their images, they identified redshift 10 to redshift 13 galaxies in their images, which they then followed up with the near-spec telescope instrument, and they got these breaks and confirmed spectroscopically a redshift 13 galaxy. And so we are looking so much further back in the universe and higher redshifts than we thought was going to be possible in the first few years. And the JADES team has some of the deepest observations and longest exposures. And so they're able to see a lot of these really far away galaxies, which is incredible and exciting. We can also use something called a GRISM, which instead of specifically pinpointing which galaxies we want to look at, we get a spectrum of an entire field of view. So you basically take a prism and you disperse the light of everything in your image all at the same time. And the Eiger collaboration had a really great program where they got spectra of, again, this GRISM spectra of an entire kind of image of galaxies, and we're able to identify through these really strong emission lines 117 galaxies without ever having to find them first in the images. They found them in the spectra first. And so this is building up statistical samples of spectroscopically confirmed galaxies, and these are all above a redshift of 5 to 7 here in this particular case, given their observations, that we just did not have before. We did not have large samples of spectroscopically confirmed galaxies above redshift 5 pretty much anywhere. And these programs with the GRISM, like Eiger, are doing an amazing job of really providing a lot of information for us to study galaxies in a large context that we were not able to do before. So what in particular have I been doing with this telescope, or what else are we finding? We're not just finding the sources and confirming the redshifts. And again, I will show this image where this is that record-holding galaxy before from Zitron in 2015. This is the one that I found with the Keck Observatory. We didn't just confirm the redshifts of both of these sources. So these sources are both at a redshift of 8.6 or so. We looked at all of these sources that I had targeted with the Keck Observatory, and we found that 3 of them are at a redshift of 8.67, and that 2 of them are actually at a redshift of 7.8, which is not disappointing because we knew about a lot of redshift 7.8 sources in this particular spot. And we can add 2 more to that, as well as we found in the imaging with CEERS and followed up with spectroscopy an additional number of redshift 8.6 to 8.7 galaxies. In fact, there are probably more as of right now, but as of just our CEERS observations, there are 9 confirmed 8.7 galaxies in the EGS field. When 2 seemed like an abundance, 9 is confirmation that there is definitely an abundance of sources in this particular spot from what we would expect. But did we just find the galaxy, or did we just measure distance? No. In fact, we found out something really interesting about some of these sources. This is that same image that I showed you before, where it was kind of just a blob in Hubble, and now we actually can see features. There's 3 components. There's 3 bright spots in this particular galaxy. This is that same Keck record-holding galaxy at 8.7 in the EGS field. But with the observations from JWST that covered all of those wavelengths, and we actually got to see the detailed structure of this source in the imaging, we also got detailed in the spectra that we didn't necessarily expect to see. In fact, the hydrogen emission line had a second emission component that was much broader than the star formation. Just the stars alone would emit hydrogen in this kind of shape, which matches a lot of the other emission line features in our spectrum. But there is a second source that's emitting this hydrogen emission line here, but it has a broader feature. And through a lot of analysis and arguments, we determined that this yellow feature here is actually coming from a black hole that is actively accreting material at the center of this galaxy here in this bright component in the middle. So we found a black hole that existed at redshift 8.7, which was less than 600 million years after the Big Bang. That's quite bright. And so this was the paper that I put out last year about this particular source, and then did what we learned from NearSpec. And why is that interesting that we found a black hole? For a lot of reasons, and it's exciting in and of itself. But for example, we are talking here about the Big Bang here on the left this time, and then then we have time is passing. We haven't quite gotten to present day over here, but let's say about a billion years after the Big Bang is about in this regime. And all of the other active supermassive black holes or active galactic nuclei or AGN are shown here. These are detected by a lot of other telescopes. The y-axis here is the size. How massive is this black hole, the supermassive black hole at the center of this galaxy, as a function of like how big it is compared to the sun. And so you can see that there's a lot of incredibly bright, very large supermassive black holes in these what we call quasars here, and we just did not have any observations of fainter things around this time, or really a whole lot of fainter objects in general, because again, it's easier to find the bright things, and with our sensitivity improvements to GWST, we're able to detect things below the observations that we found before. So these smaller and fainter supermassive black holes. And not just did we find it, it's actually the most distant one that we found at the time. And so by quite a bit, we were not able to see the black holes or measure them in any kind of way due to a lack of spectroscopic data at these redshifts. And we also aren't quite sure how these black holes got to be this large this early. This is still only 700 million years after the Big Bang. These are redshift 7.5 quasars that have been found. And they have been followed up by the Aspire team with GWST. If that is something that you're interested in, I highly recommend you look it up because they have some great data. And so this is just a less graphically appealing way to look at this particular data set. But again, at redshift about 7.5, these are those bright quasars. So these green points are akin to the purple that you saw in the last one. And then here again, as a function of black hole mass and redshift, this is this object that we found and measured here. We're not sure how these black holes got this big this fast. There are a couple of different methods to make a black hole and to grow it larger. And this particular galaxy, while it is a fainter black hole, it is larger than we can physically explain very well with the short period of time that it has had to grow since the Big Bang, since galaxies formed. And so there are a couple different ways that could have happened. I was, grateful, I guess, to have broken a record, but I was more excited that we were able to do this and to have my record broken. In fact, that happened very quickly because GNZ11, this is that record-breaking galaxy from the Hubble era. We had this beautiful, beautiful spectrum from the JADES team. It has features in it as well that are indicative potentially of an active galactic nuclei, an AGN, or an active black hole in the center. And that's right here. It would be a smaller one, but it existed quite earlier. We have a couple other galaxies that we've found with GWST and have followed up and found these features that indicate that there is an active black hole. And so we are starting to fill in this portion of this kind of figure and this area of study of how did these galaxies form and grow and what are they like, and putting them into context is really important to us. We also want to understand how did black holes in the center of galaxies grow, and we've not had any data. These are some of the first actual data points that we can use to compare to theory. And so I'm excited, of course, to use this telescope and all of the really exciting things that we're finding. It's possible that these black holes are actually ionizing more of the universe around them than just the star formation in the galaxy. And that's why, from sources like this one, we are able to see Lyman alpha because it's ionized enough of a region around it, even though it's quite early. And there's a lot of science and studies still going on that have really revolutionized a lot of science. And I will just leave this up. This is the first half of the cosmos field. The entire image here in the background is one continuous image with GWST that we took over several filters, and it's impossible to really understand the scale without zooming in. And so this is, again, just half of the cosmos field that covered a large area. And I said it was there to look for the bright, rare objects. And that is relative because I will zoom in a little bit more here in a second, and you can see that you can zoom in and see a lot of objects. You don't just necessarily see only really really bright sources. Again, anything with spikes is a star in our own Milky Way that's in the way of us taking images out into the universe beyond. And we do have the other half of this data that's being processed, and hopefully we'll release all of these things soon. There are a couple gaps that you might notice in this particular case. This was a pointing that failed and will be retaken, and so those will be data that will be observed coming up in the next couple months, and so we can finish filling out the entire area of the sky. And it is impossible, again, to tell you everything that we have found, or even everything that we have learned about the early universe. And I elected to mostly share some really incredible major collaborations and their main discoveries in my particular field of early galaxies in the universe. And I highly encourage, if you are interested, to look up some of these programs, some of these press releases, and really dive deep into the images or the science. And feel free to ask me, questions about any of them. This is just one small field of astronomy, and it has truly exploded with this telescope. And there are many, many more fields that have been fully revolutionized with the telescope that is technologically incredibly sensitive and giving us a view into the universe that we've never had before. And so this is just but a small portion of what we have been able to do in astronomy with this new telescope. And I'm happy to get to show you a small, slightly in-depth look at that, as well as any of the really cool discoveries that we've been making. So with that, I will stop talking, and I